So today, this is outline of today's lecture. I will introduce what is propositional logic, and then the syntax of propositional logic. And if time permits, we will go into natural deduction. Okay. So probably we'll touch very basic about intro to natural deduction. Okay, so what is a propositional logic? It's a very brief one, and we are going to cover in more detail in the next few lectures. So what we want to do is to focus on the declarative sentences. Okay, so if you took English or language art class, you know what is a declarative sentence. So the one that you see on the left-hand side, a declarative sentence, it can be either true or false. Right? The sum of numbers 3 and 5 is equal to 8. Is this true or false? True, true. Jane reacted violently to Jack's accusation. True or false? We don't have enough information, but it should be either true or false, given the enough information about this description. All Martians like pepperoni pizza. True or false? This is true if there is no Martian, which is a bit counterintuitive, but you will learn the data. Okay? If there is at least one Martian, then you have to prove it, whether all Martians like pepperoni pizza. Okay, so anyway, that's not about the subject of this course, whether there is a Martian or not. But the point is, these sentences are the ones that can be either true or false, okay, given enough information. Actually, that's not necessarily true. The last one is not. So the last one, actually no, this can be still. So every even natural number is the sum of the two prime numbers. So this sentence is very mathematical, so there's no ambiguity. Okay, unlike the Martian example. Okay, so you know what is an even natural number, right? So what are the even natural numbers? 2, 4, 6, 8, and so on, right? Okay. And what is a prime number? So what is the definition of prime number? Prime number, what is a prime number? Anyone?
It can only be divided by itself and 1.
So he was saying that the number that can be divided by itself and 1. But what about 1? The 1 can be divided by itself and 1. So is 1 a prime number? Is 1 a prime number? No. 1 is not a prime number. So that definition, this definition almost worked except for 1. So the prime number is greater than 1 and has only two factors, 1 and itself. That's a prime number. So 3, 5, 7, 11, 13, 17, 19, so 23. 29, so those are the prime numbers. Okay, so the sentence is saying that every even natural number is the sum of the two prime numbers. True or false? False. Why is it false? So what is the counter example to this claim? 1. 1 is not an even number. We are talking about all natural, even natural number is the sum of the two prime numbers. Okay, so but 1 is not an even number, so we don't have to care about it. So recall that this sentence is basically if-then clause, as we learned before. So if some number is even natural number, then that number should be represented by the sum of the two prime numbers. True or false? False. What's that false? Why is it false? So 2, okay, so he's saying 1 plus 1 equals 2. What that means here is 2 is an even number, right? But 2 can be represented in sum of the 1 plus 1, right? That's the only way that you can add up to 2, right? If you don't count maybe zeros there. So, but 2 equals 1 plus 1. The 1 is not a prime number, right? So that's not a valid thing. So 2 equals 0 plus 2 does not also make there's no way that 2 can be represented by the sum of 2 prime numbers. Right? Okay. So that is false. Because we found one counterexample that 2 is an even number, but there is no way to represent 2 as the sum of 2 prime numbers. Each of them must be a prime number. There is no way to do that. Okay? Good. So maybe that is because only about the 2. So let's actually say this. Every even natural number that is greater than 2 is the sum of the 2 prime numbers. Let's modify that so that counterexample is no longer a counterexample. Okay, let's ponder on this one. Okay, every even natural number is the sum of 2 prime numbers. True or false? False. Is that false? Example?
Like I say, like 2 is equal to 1.
Yeah, so that is, okay, so that example is no longer a counterexample to this, because what we said is if the number is even natural number that is greater than 2, then that should be, that can be represented as sum of 2 prime numbers, right? So now if condition is now, doesn't hold for this example. So if condition is saying if you have an even number that is greater than 2, then that can be the sum of 2 prime numbers, right? Do you see the difference when I switch this sentence to be including this condition? So the condition is basically saying if some number n is an even natural number greater than 2, then n is okay? So this is the new sentence that we're talking about, and I massage the sentence into if-then way so that you can easily see what is the condition that you're keeping. So true or false? That doesn't seem obvious, so why don't we just play with some example? Okay. Can anyone give an even number? 50. 50? Okay. So 50. Can we write 50 by adding 2 prime numbers? 31 and 19, that's good. Okay, yeah, that's 31 plus 19 is actually the 2 primes, right? And then they add up to 50. Okay, so that didn't work. Let's try something else than that. So let's go from the smaller numbers. Okay. What is the even number that is greater than 2 but is smallest? What is it? You can just say that. This is actually not very tricky, right? What is even number that is greater than 2 and smallest among them? 4. Okay? So 4 can be represented as the sum of 2 prime numbers. Yeah. Okay. Let me actually close this. Okay, so 4. 4 is equal to, what are the 2 prime numbers that add up to 4? Not 2 different prime numbers. We didn't say these 2 prime numbers should be different, right? So 4 is equal to 2 plus 2. Okay? So that seems to be working. What about 6? 3 plus 3. Right? Okay, so 6. What is the next? 8. 8 is 3 plus 5. 10? 5 plus 5. Okay. Are we just lucky? 5 plus 7. Okay. So initial fragment of the numbers don't seem to contradict the claim, right? Okay. So is it really true or false? So that's a bit tricky because this sentence has no ambiguity. You know what is an even number, what is a natural number, you know what is a prime number. But then it's not easy to see why this is true or false. And what is most surprising is nobody knows the answer yet. Even the best mathematician in the world doesn't know the answer. Okay? What is the name of this conjecture? Anyone knows? Okay, this is called Goldbach's conjecture. Okay? Very simple problem, but nobody knows the answer. So, why? So why don't we just try these things? So I showed some of the numbers work, right? So can we just continue this and this can be a proof? Infinity many, so can we, what is the issue? You cannot enumerate all possibilities. Even if you enumerate this and show that this sentence works for n equals like 1,000 million, okay? You still cannot say that this is true because you didn't exhaust all the even natural numbers. Okay, so who knows? There may be some counterexample later. Indeed, in mathematics, that kind of thing happens often. People thought that this is a conjecture that must be true because people tried many examples and there was no counterexample. But then there's also no proof. Okay, so people believe that this must be true, but then according to the principles of mathematics, the question is left open. Okay, this is one of the such problems. Nobody knows the answer yet. Okay. All right. Oh, by the way, what we want to say here is we are going to consider the sentences of this kind where we can say we don't know whether this is true or false, but in principle that should evaluate the true or false. These are the sentences that we are considering. And non-declarative sentences like imperative or questions sentence, those sentences we don't care. Okay, we cannot actually assign the meaning to those sentences in logic. So if you say, could you please pass the salt, is it true or false? It's very silly to say that. And ready, steady, go, or may the force be with you. This is not a sentence that you say is true or false. Okay, so for the time being, we will consider only these sentences that we can assign true or false. And there are many logics that allows us to say that. And propositional logic is the simplest logic of all kind. And this is the foundation of many other logics. In this logic, you're going to have something called atomic sentence. So atomic sentence is the smallest unit that you can assign truth values, either true or false. Okay, so for this, for here I have some examples. P is an atomic sentence, okay, that represented I won the lottery last week. Okay, so it can be either true or false. Let's assume that this is the smallest unit that we can assign the truth value. Another thing is Q. I purchased a lottery ticket. Again, this can be true or false. And R, I won last week's sweepstakes. So these sentences can be either true or false. Okay? And then in this logic, we have something called connectives. Negation, disjunction, conjunction, and implication. And these connectives are used to combine the atomic sentences to say something more complex. Okay? So that's very intuitive, and this is why the propositional logic is intuitive to represent the human reasoning. So when you say negation, this is opposite. So when we say P represents that I won the lottery last week, then negation of that sentence is I did not win the lottery, right? Easy to see. Disjunction. So if you say P or R, it means I won the lottery last week or I won the last week's sweepstakes. Okay? So or is also a common word that we use in English. Conjunction, and, right? So we say P and R. Okay? So I won the lottery and the sweepstakes last week. There's also implication, and we talk about implication quite a few times by now. P implies Q. And this is if then clause sentences. So if I won the lottery last week, then I purchased a lottery ticket. We can write the English sentence in a lengthy way, but we can also write in terms of these formulas. So like P implies Q. Okay? So after this, you can build many other more composite formulas. So P and Q implies not R or Q. Okay, so that means what? If I won the lottery last week and purchased a lottery ticket, then either or both, I did not win last week's sweepstakes, or I purchased a lottery ticket. So very lengthy sentences can be represented as a formula in this succinct way. Okay, there are some connective property priority where negation bind more tightly than conjunction and disjunction, and these bind more tightly to implication. Don't worry about this now. We are going to look at the syntax more carefully. Okay, so that I will revisit this at that time. Okay. So here is the example from the textbook. So the example is saying that if the train arrives late and there are no taxis at the station, then John is late for his meeting. So that's one clue that you know. Another clue is John is not late for his meeting. And the last clue is the train did arrive late. Now, the sentence here is there was a taxi at the station. Is it true or false? Given the three sentences above, can we say that there was a taxi at the station, or this does not necessarily true? Okay, so let's open the subtractive. It is true or false question. Was the taxi at the station true or false? Okay, are you done? Okay, so let's see. Interesting. So 76% said true, 24% said no. Question? Were you here last time? No, you can talk later after the class. Okay, so okay, so a quarter of the group says false. Okay, let's see what is going on. So the answer is actually true. Okay, so why that's the case? Let's try to use the propositional logic. Okay, so what we are going to say is we are going to introduce the proposition. So let's try to write it in a formula. So let me denote this train arrived late as TL. Okay, so this is an atomic sentence. And taxi at the station, there is a taxi at the station saying T. Okay, and John is late, say John late. Okay, so this first sentence is saying train arrives late and there is no taxi at the station, meaning that negation of taxi. Okay, then John is late for his meeting. So the first sentence can be represented by this formula, right? Okay. The second one is John is not late for meeting, can be represented as this one. Okay. Train did arrive late is TL. So you know these three facts, 1, 2, 3. And the conclusion that we want to check is if there was a taxi at the station. Okay? So in the case, in terms of proof, the first three sentences are called premise. Okay? These are the assumptions that you are given. Okay? You don't need to prove this is true. This is assumed to be true. But what you have to show is whether the last sentence, the conclusion, follows from 1 to 3. It's similar to this Lewis Carroll puzzle that we talked last time. Okay? Does this conclusion follows from the three sentences? If you assume the first three sentences, should you believe that the last sentence to be true? So there are actually a few different ways to prove it. One way is so-called proof by contradiction. Okay, so what that happens, we will actually go over the detail later, but basically what it says is we don't know whether there was a taxi at the station, but let's try to assume this is false and see what happens. So instead of this, let's try to assume this together with this one. Okay, so for the sake of contradiction, we'll assume that there was no taxi at the station. Then what happens is we know that train arrived late, and also we know that we assume that there was no taxi at the station. Then this if condition becomes true, right? So what can you conclude? If you know TL, and if you know that not TL is true, and also you know that this if then sentence is true, what can you conclude? John is late, right? Because TL and not T is true, so this antecedent, this condition is true. This condition is true, so this conclusion follows. So John is late. But at the same time, you also know that John is not late. So these two cannot be true at the same time. So contradiction. So where this contradiction comes from is because we assume arbitrarily that there was no taxi at the station. This is the culprit. So in that proof, what happens is we say that this is actually false, because once you assume that, there's an inconsistency. So you conclude that actually there was a taxi at the station. That's actually what you do in reasoning, right? So even without using these symbols, you basically say, oh, what happens if there was a taxi? If there was no taxi at the station, then from the condition that train arrived late, and also there's no taxi at the station, I can see from the first sentence John should be late for his meeting, but I also know that John is not late for the meeting. That cannot be true. Okay, that's what you do in your reasoning. Okay, and what we are going to do in the proof of this theorem or this property is basically the same as what we do informally. Okay, we just try to make it as a more formal so that we can easily calculate this. Even computers can calculate this kind of reasoning. When we talk about this microscope idea, so eyes are good at seeing a variety of things at the same time, but it's not necessarily good at seeing the very small pieces, right? So logic is similar to that. Your intuition is actually a very good guide, but sometimes it's misleading. So when you try to make those deduction steps more sound and more mathematical, then you can compute in computers, and that actually gives a very interesting computation test. All right, the next one. If it is raining and Jane does not have umbrella with her, then she will get wet. Jane is not wet, it is raining. True or false? Jane has her umbrella with her. Let's do one more time. Okay, so are we done? Let's see. Okay, so now 95% is saying true and maybe 1% says false. Okay. Yeah, so the answer is actually true, and in fact, you will probably realize that it's actually very similar to the previous problem, right? Okay. So what is going on here? Let's say that if it is raining, say raining, have umbrella, let's say U, and she will get wet as W. So the first sentence is saying that if it rains and Jane does not have umbrella, then she will get wet. And Jane is not wet, so that's negation of wet, and it is raining. Okay, so from this, can we conclude that Jane has an umbrella? The structure of this problem is actually exactly the same as the previous one. In fact, this is actually the comparison between the two. Okay? So if you just say P to represent the train is late, versus maybe in example 2, it is raining. And Q in example 1 represent that taxi is at the station, and example 2 Q represent Jane has an umbrella with her. R in example 1 means John is late for the meeting. R in example 2, Jane gets wet. And once you write this in English, you get this sentence, and then basically you can also write this as the this way, right? So we just change the symbols. Okay, John late, instead of John late, we say P. Okay, and similar for the other symbols. But other than that, this actually is exactly the same formula. Okay? So it's interesting that these two seemingly different problems actually shares the same underlying structure. Okay? All right, any question up to this part? So we just finished the introduction to propositional logic. So this just gives you some flavor about propositional logic. The next section is about the syntax of propositional logic, and we are going to go a bit formal here, right? So be ready for these things. So we are going to define a language, and whenever we define some formal language, we have to define two things. One is syntax. How do you write these language syntactically? And then the semantics. What is the meaning of that sentence? Okay? So you can think about this as just natural language like English, French, or Chinese, or whatever. Okay? You first need to learn what is an alphabet. So alphabet of propositional logic has multiple components. The first one is called the propositional signature. Okay? So we already saw the, these kinds of things in the previous slide: P, Q, R, or J, L, R, U. Okay, those kind of atomic sentences. Okay, so they are called atoms. Okay. The next one is called the propositional connectives. And note here that these connectives are not part of the propositional signature. Okay, so propositional signature is like PQR, but the connectives are distinct from those things. Okay, so there are multiple connectives. Based on the number of arguments that these connectives can have, we can say binary or unary or zeroary connectives. So the first binary means that there are two arguments. Okay? So conjunction, disjunction, and implication will have two arguments. And the unary negation applies to one argument. There are also something called zero-place connectives called bottom and top. Okay? Again, don't need to worry about the meaning of these things yet, because we are not talking about meaning now. We are talking about the syntax. It's just an alphabet. So the whole alphabet consists of these things. You can use any atoms from the given signature and the propositional connectives and parentheses if needed. Okay, these are the symbols. Of course, if you just enumerate symbols in arbitrary sequence, that doesn't necessarily mean the propositional formula. Okay? So when you say a string, it's just a finite sequence of this alphabet. Okay? But what we are really interested in is what is the sequence that actually makes some sense. So we are going to define something called propositional formulas. And these formulas are built by applying some rules. Okay. So here's a definition, and we're going to have a piece after this one. Okay. Not a gradable piece, but for the substantive. Propositional formula of signature sigma is defined recursively as follows. First, when you write any atom itself is a formula. So if your signature contains PQR, you can just write P and you can claim that this is a formula. It's an atom, but there is also a formula. Both zero-place connectives are formulas. So in the previous slide, there were two zero-place connectives, bottom and top. They are formulas too. Okay? So the first two cases are kind of base case. And then the next is recursive case or inductive case. What that means is, in order to define a formula, this definition will call the same kind of definition. So it will call the definition again. That looks somewhat strange, but that's how the recursive calls are being made. Okay. So what is the thing here? If f is a formula, then we can construct another formula that is negation of f. In other words, if you want to say that something of the form negation of f is a formula, then you have to make sure that f is a formula. Okay? So it's actually going both ways. If you happen to know that f is a formula, then you can find another formula by putting the negation and the open and closing parentheses. That gives you another formula. Okay? Same as this. So instead of writing all the binary connectives, I use this meta symbol, this sun. If you have a formula, f and g happen to be, those are the formulas, then you can write another formula starting with open parenthesis, f followed by the binary connective, followed by g, followed by closing parenthesis. This is also a formula. Okay? So although I wrote only one symbol here, this actually stands for all the binary connectives. Okay? And in the book, and this is also called well-formed propositional formulas. I'm not going to distinguish between well-formed. I'm going to skip the word well-formed here because there is no ill-formed formula. Okay. Any question up to this part? So, one question: how many formulas are there in the world? How many formulas will be there? Infinitely many, right? Because you can construct formulas over and over, right? So let's say, if you know that P is a formula, you can say not P is a formula, right? And you can also put another not here. This is also a formula, right? Because by definition, if you know that P is a formula, then not P is a formula. If you know that not P is a formula, then putting another negation in front also makes another formula. And you can continue this forever. Right? And also, if you know that this is a formula, then you can combine with another formula. Right? Okay? By using the last clause. If you know that these two are formulas, you can combine these formulas using binary connectives. So you can actually build many, many such formulas. Now, one thing that I want you to be careful before we do the problem in the next slide, I want you to be careful for the time being that parentheses play a very important role. So don't skip the parentheses. So when I say negation of f is a formula, it should start with the open parentheses and end with another parenthesis. And when you say the binary connective, we are not skipping any parentheses for now. Okay? So there's no skipping of parentheses before we actually introducing the precedence of the operators. Okay? Are we ready to go? Any question up to this part? Okay? All right. By the way, this is a recursive definition, and recursive definition occurs very often in the computer science. And this is actually very powerful. So even if there are 4 lines here, you can define infinitely many formulas. So recursion is one way to close the gap between finite cases versus infinite cases. Okay. We'll come back to this issue soon. Okay, so I want you to tell me whether each of them is a propositional formula or not. Okay? Is this a propositional formula? How do we know that this is not a propositional formula? How do we prove that this is not a propositional formula? So I showed you the rule in the previous slide, right? Okay, and the question is whether this is a formula or not. Okay? How do we, and the answer seems to be that this is not a formula, right? But how do we prove that this is not a formula? Somebody will explain.
That's the negation doesn't have a formula.
So the argument here is negation has nothing together, but is it really easy to see? So in order to say your reasoning, you're actually looking at this case, right? What if f is empty string? Then can it be like this? How do we know that f is not an empty string? How do we know that f is not an empty string? A formula cannot be empty. How do we know that?
You can only negate something that's already a formula, so if it wasn't a formula, then you could use negation as a formula.
So, but yeah, if f is happens to be an empty string, and if empty string is a formula, then this occurrence can happen, right? In order to say that this occurrence cannot happen, you have to prove another property, that a formula cannot be an empty string, right? So this is actually not very trivial. Okay, let me ask you, what task is easier? To show that something is a formula versus to show that something is not a formula? What is easier job for you to think about?
Not a formula.
Okay, any other opinion? The answer is actually opposite. If it is a formula, all you need to do is to show a way to construct that formula. If it is not a formula, then what you have to show is no matter what combination of rules that you apply, there is no way to generate a string. That's much harder because you have to show all possible combinations of rules. You cannot generate such string. Okay. All right. So this is actually not a formula, and maybe for now we can use the intuition. What happens is when this string becomes lengthier and complex, then the intuition does not help much. So you have to use some mechanized tool, some algorithm, or some program to check this. Okay. And obviously, how do you write a proof? How do you write a software to check this? Whether this string is a formula or not. This is actually interesting programming exercise to do. Now for this one, okay, it's not a formula. So here's some informal reasoning. Okay, if you look at the clauses here, okay, there are 4 cases. Any formula belongs to one of these 4 cases. It could be an atom, it could be zero-place connective, or it could be starting with open parentheses followed by the negation. Or it could be starting with open parentheses followed by something and then followed by binary connective. Now if you look at this one, it doesn't match the patterns of the first 2. Because first 2 cases, atom or zero-place connectives, they do not have parentheses. So it could be either the 3rd case or the 4th case. If this is an instance of this, okay? If this is a formula based on the 3rd rule, then it has to match this pattern. Meaning that this is first character here, the 2nd character here, okay? And this must be F, and there must be actually closing parentheses. As you see, actually, even I don't need to even bother with what is F. There is no ending parenthesis. So this one cannot be generated from the 3rd case. Are we together? The 3rd case, for this to be a formula, you have to start with open parentheses and end with another parenthesis, right? But this string that you have doesn't have closing parentheses. So it cannot be generated by the third rule. Same as fourth rule does not apply here, because fourth rule also start with open parentheses and end with closing parentheses. Okay? So this is a very simple proof saying that why this string cannot be a formula. There is no way to apply these rules to say that this is a formula. Now we are lucky actually, because it happens to be the case that there is no closing parenthesis. If there is a closing parenthesis, then our task is reduced to prove that whether this guy inside is a formula. Okay, and you have to go recursively. So then the question is whether this f, this is not. Whether this is a formula. Okay, and then you have to do this checking recursively. Can it be generated by the first clause, second clause, third clause, fourth clause? Okay. All right. So that's actually how you write the program to compute. But since you're human, you don't need to do that. Let's just use intuition for now. Okay. Is this a formula? Is this a formula? True or false? What is your intuition saying here? It's false, right? It's not a formula. What about this? It's not a formula, right? What about this? This is not a formula. Why? What?
Because we can't prove that their P exists.
P is a formula.
There's no
P is an
parentheses.
electron. There's no parenthesis, right? In order to have negation, according to the rule that we just talked about, if P is a formula, then we can write another formula by putting negation and also putting open and closing parentheses. I told you just before that we will not skip any parentheses. Okay? So for now, according to the definition, if we follow the definition precisely, then this is a formula, but this is not a formula. Okay? Okay. Okay. So let me say that this is not a formula, not a formula, not a formula, not a formula. What about this? Okay, maybe let me just show you all things here. Okay, and I will actually copy this too. So choose from 5 to 9. Okay, let's see. Actually, choose all that are propositional formulas. Okay, so let me do this. It's a short answer question. So show everything that is a formula. Just write the numbers of them. Okay, so let's see. So okay, so these are the answers that I see. So 5, 7, 8, 7, 8, 9, 7, 5, 7, 7, 8, 9, 6, 7, 9. So 5, 7 seems to be very common. 9 is also very common too. Okay. Unfortunately, I see only 1, 2, 3, 4, 5 solutions correct. All others are wrong. Okay, so let's see what is going on here. 5. Is 5 a formula? It is not. Okay. So why is that the case? It doesn't conform to any of these patterns. So look at the right one, right? So this one is not an atom, right? And it's not a zero place connective alone, right? Because here, only bottom or top can be the second case, right? Okay, what about the third case? In order to have third case, you must have a negation, but this one doesn't have any negation. For the fourth case, it should have binary connective, it doesn't have. So this is not conforming to any of the patterns here. Okay? So if you ask the syntactic check on this, suppose we write a program that checks the syntax of the formula, and if you ask them, it's a syntax error. This is a zero place connective, but there is no parenthesis. The second case doesn't have any parenthesis, right? Okay. So that's not. Okay. What about 6? Some people answered 6, although there are many. This is not a formula because if you have to, so the closest thing could be this last case. So the last case we need a parenthesis. Okay, the formula in 6 or the string in 6 does not have parentheses, so it cannot be a formula. Okay. What about 7? Like randomly flipping it. What about 7? 7 is actually a formula. Why? Because we can actually apply the rule. So P is a formula, right? No idea why it's flipping. So P is a formula, right? And Q is a formula, right? Because of the first condition, case, right? If P is a formula, then our third case is saying that now P of the parenthesis is a formula, right? And then we also know from the first case, this is a formula, then this is a formula, then there, disjunction is a formula. Okay? And that's what the string in 7 is saying, so 7 is a formula. I told you that what is easier to do, to show that this is a formula, we just need to apply the rules to show that this is a formula. Okay, good. What about 8? 8 is not a formula because it has unnecessary parentheses. Okay, so this is not a formula. Okay. And 9 is not a formula either because it does not have parentheses. I don't know what is going on. Okay, so among the last 5 formula strings, only 7 is a formula. Okay, are we together? Okay, it's a bit tricky because we are not skipping any parentheses. We are trying to be dumb. Okay, so suppose we have encoded this definition in a computer, and computer will say yes or no based on the rules only, right? It doesn't use any convention that you guys are already used to, which is to drop some parentheses And you are told when you are young that you can use as many parentheses as necessary if it doesn't confuse you, but that's not the case here. Okay, we just follow the definition precisely. Okay, now something that I just spoke. If it is a formula, then you can use the rules to show that this is a formula. So one way to make that easy is to draw the parse tree, so-called parse tree, which is very common in computer science. And what that means is we are going to turn this into a tree structure so that this tree structure represents the application of the rules. Okay? So the rule will be, the tree will be looking like this. So this is a formula. So if you look at this, this is of the form F implies G, right? So implication is so-called outermost connective. So this becomes the root node. Okay, and the left child will represent tree for this formula. The right child will represent tree for this formula. And this goes recursively, okay, meaning that it will do the same thing over and over. If you look at this as a formula, the outermost connective is conjunction. Okay? And then the left node of that conjunction is this formula, and the right child is this one. So we are going to write this one, and actually this one is negation. Okay. Okay. Okay, so this is negation and P. Okay. And on the right hand side we have this formula. The outermost connective here is also conjunction, right? So this conjunction. Left hand side is P here, so I write P here. On the right hand side we have Q or not R, so the node here is disjunction. The left is Q, the right has negation and R. Okay, so I didn't copy the parentheses because it actually makes clear that where should be the parentheses. So for this tree representation, you can actually do this parentheses, but that's going too much. So I skip writing the parentheses here. Okay. All right. Actually, this is overlaid one. Let me actually erase what I wrote so you can easily see. Okay, so this is the same tree that I draw. Now this definition of a subformula. So what is a subformula? So these are the formulas that are contained in another formula. So the definition here is subformula of phi are the formulas corresponding to the subtrees of the parse tree of phi. Okay. So whatever that is, there is a formula that we are given here, and there are many subformulas that are contained in this formula, right? So one question that I can say is a formula a subformula of itself? If you just follow the definition here, can you say a formula is a subformula of the same formula? True or false? Okay, this is actually true, and that the reason for that is when you say subtree, it's actually going back to the definition of subtree. A tree is a subtree of itself. Okay, if you have seen the graph theory in discrete math, there's a tree and subtree relation, and there a subtree is a tree of its a tree is a subtree of itself. So the same definition applies here. So a formula is a subformula of itself. My next question is actually this one. Okay. So I just told you the definition of subformula. Okay. So how many subformulas are there for the given one? Okay, so let's. Okay, so all right, so let's see what you said. Majority chose C, so you're saying that there are 11 subformulas. So let's count them. Okay, so it should be a subtree, and it should be a formula that corresponding to the subtree, right? So first, P is a subformula, right? Because P is a subtree, right? Good. What about not P? So not P is also a subtree here, right? Okay, let's see. Okay, so now P is also a subformula. Q is also a subformula. Okay, and let me actually say the atomic formula too. So P already counted, Q already counted. So R is also a subformula. Okay, and not P and Q. So this subtree. So not P and Q. This is also a subformula. So we cover this. And not R. So not R is also a subformula. Okay. And Q or not R. So Q or not R. This is also a subformula. And P and Q or not R is also a formula, so I cover this guy. And then the whole formula. Okay, so now P and Q. Okay, so the whole thing is also a formula. So how many are there? 9. Okay, 9 is. So some of you probably counted twice for P and Q, but I asked you about the formulas, not the occurrences of formulas. So the correct answer is actually 9. Okay. All right, so, okay, now I'm going to release you. You don't have to worry too much about the parentheses. Okay, so let's adopt this convention. So the binding power, here the negation binds more tightly than disjunction and conjunction, and disjunction and conjunction binds more tightly to, than implication. And implication is right associative. So if you remember what these are in algebra, right? If you have seen, so if you see this kind of thing, it could be ambiguous whether it means either P implies Q implies R, or whether implies this, right? So because I skipped the parentheses, it's a bit confusing which one that it represents. Okay, and each of them has different parse tree, and ultimately it will have different meaning too. So this is actually usually not a good way to write the grammar, but we are going to introduce the convention. If you see this kind of thing, we are going to say the parenthesis is going to be on the right first. So if you see P implies Q implies R, we'll say Q implies R is going to be evaluated first, and then the next one. This is called right associativity. And if you see that like this thing, okay, again it is confusing whether do I really mean that P and Q implies R, or do I mean P and Q implies R? Oops. Okay, so this string can be ambiguous. It means either this or that. Okay, if we don't use the parentheses there. But what we are going to use as a convention is conjunction binds more tightly than this one. So if you have these two occurrences, this binds more tightly. So we'll understand this string as this one, not the other one. Okay. So if you don't follow this convention, then you're going to understand the same formula in different ways, and that's actually bad, because what often happens is you write some property as a formula, and computers can check whether this property is true or false. But what you intended is not the same as what computers will evaluate. Okay, that may create a lot of bugs in the software design. All right, so any question up to this part? Okay. Okay, so I think we are done. So here we are done with the propositional logic syntax. And as I expected, we don't have time to go into the natural deduction, so that's the topic that we are going to cover next class. Okay, so let me open the software page and we can finish up here.